Hello. So welcome to class, and today is we're going to go over the 2017 AIME 1, and we're going to start on question 5. All right. All right. So I'll start going over this problem now. So you have a rational number that's written in base 8 as ABCD, and all the digits are non-zero. And the same number in base 12 is BB.BA. And so you want to find the 10-digit number ABC. And so you can look at these two numbers and you can see that the parts before and after the decimal points must both be equal to each other, because the parts after the decimal point must in total have a total sum of less than 1. And so you have that 8a plus b equals 12b plus b, and c over 8 and c over 8 plus d over 64 equals b over 12 plus a over 144. And so the first equation, we can cancel out these b's, and so a is equal to 1.5b. And for this equation, you can plug this into the second equation. And what that will tell you is that c over 8 plus d over 64 is just equal to b over 12 plus 3a over 2 times 144, which is 3b over 32 when you simplify this. And so you can multiply both sides by 64 now. And so what that tells you is that 8c plus d is equal to 6b. And so because you have that a is equal to 1.5b, from here you have that ab can either be 3, 2, or it can be 6, 4. And when you plug in b equals 2 to here, you can see that there's only one solution for c and d. And when you plug this back into here, you can find that it fails. Oh, sorry. And so when you solve this, you can get that c equals 1 and d is equal to 4. And so when you plug this back into here, it works. And then that tells you that ABC, the 3-digit integer ABC, is equal to 321. And so the answer, sorry. And so the answer is 321. So does anyone have any questions about this problem? All right. So I'll start going over this problem now. So you're given a circle that's circumscribed around an isosceles triangle, and the two congruent angles of the isosceles triangle have degree measure x. And then you choose 2 points independently and uniformly at random on the circle, and you draw a chord between them. And so you want to find the probability that the chord and so the probability that the chord intersects the triangle is 14 over 25. And so what you're trying to find is the difference between the largest and smallest possible values of x. And so first of all, we can draw a diagram. So you're given a circle and it's circumscribed around an isosceles triangle. And the two congruents have degrees x. And so the probability that any point selected at random is in this arc is just x divided by 180 is 2x divided by 360, or x divided by 180. And similarly, for this arc, it's also x divided by 180. In this arc, the probability of it being selected is 1 minus 2 times x over 180, or 90 minus x over 90. And now, the probability that the two randomly selected points are on this arc and this arc, which is one of the ways in which the chord can intersect the triangle, is 2 times x squared over 180 squared. And the probability that the chord has 1 point in this arc and 1 point in this arc is just x over 180, 2 times x over 180 minus 90 minus x over 90. And the same number is true for a chord whose endpoints are in this arc and this arc, so we multiply this by 2. And now we have that this is equal to just 14 over 25. And so you can multiply both sides of this equation by 180 squared. And so what that gives you is 2x squared plus 8 times 8x times 90 minus x is equal to 14 times 36 squared. And so when you move everything to one side, you get that this is just 6x squared minus 720x plus 14 times 36 squared is equal to 0. And now you can divide both sides by 6, and what that gives you is x squared minus 120x plus 14 times 6 cubed is equal to 0. And so now we can list out ways to factor this such that the sum is 120. So 14 times 216, and you can continue trying until you have that 84 times 36 is equal to 14 times 6 cubed, and 84 plus 36 is equal to 120. So the possible values of x are 84 and 36. And as a quick sanity check, both of these are possible angles in an isosceles triangle. And so the answer is their difference, which is 84 minus 36, or 0.48. So does anyone have any questions about this problem? All right. If not, let's move on to the next problem. And so once again, I'll give you guys a couple of minutes to do this problem before I start going over it. All right, I'll start going over this problem now. So you're given non-negative integers a and b such that a plus b is less than or equal to 6. And so you let t of a and b be equal to 6 choose a times 6 choose b times 6 choose a plus b. And so let s denote the sum of all t of a and b, where a and b are non-negative integers such that a plus b is less than or equal to 6. And so you want to find the remainder when s is divided by 1000. Now, to do this problem, first we can add another variable c and define it as 6 minus a minus b. And so now we have that t of a and b is 6 choose a times 6 choose b times 6 choose c, such that a plus b plus c is equal to 6. And so in it, a version of Vandermonde identity will just applying a generalized version of Vandermonde identity directly tell you that this is 18 choose 6. And if you don't know it, you can basically think of this as choosing 6 stars from this array.
I'm sorry, but are you lagging out for anyone else? Because you're lagging out for me.
Can anyone else tell if I'm lagging?
You are.
What?
A bit. You aren't lagging for me.
Okay. Basically, you can apply a generalized version of Vandermonde to 6 choose A times 6 choose B times 6 choose C such that A plus B is equal to 6, and that can directly give you the answer of 18 choose 6. And if you don't already know it, then you can just take this 6 by 3 grid, choose A stars from the first row, B stars from the second row, and C stars from the third row. And you're basically taking out a total of 6 stars from these 18 stars. And so that's just equal to 18 choose 6. And so either way, you can get that S is equal to 18 choose 6, which is 18 times 17 times 16 times 15 times 14 times 13 divided by 720, which, if you calculate it out, is equal to 18,564. And so the answer is just 564. Here when S is divided by 1,000. So does anyone have any questions about this? Okay, I guess not. So we can move on to the next problem. And once again, I'll give a couple of minutes to try this problem on your own. All right, so I'll start going over this problem now. So you have two real numbers, A and B, and they're chosen independently and uniformly random from the interval 0 to 75. And so you let O and P be 2 points on the plane such that OP is equal to 200. And so you let Q and R be on the same side of OP such that angle POQ and angle POR are A and B. And you also have that angle OQP and ORP are right angles. And so what this basically means is that Q and R on the semicircle. Okay, I'll need to redraw it. Q and R lie on the semicircle with diameter OP, such that this angle is A and this angle is B. And so you want to find the probability that QR is less than or equal to 100. And so, first of all, we can notice that QR is less than or equal to 100. This is only true. This is Q and this is R. And so let the midpoint of the semicircle with diameter OP be something like N. And then so the only way QR is less than or equal to 100 is if angle Q and R is less than or equal to 60. And so this angle is minus b. So what we are basically trying to do now is find, and you have that the absolute value of a minus b is less than or equal to 60 over 2. And so you're just trying to find the probability that this is true now. And so now you can draw a 5 by 5 grid of squares. And so this is 75 and this is 75. So each side of this is 15. And so the answer is basically this shaded in region. Just correspond to this shaded in region. And so we can complementary counts. And so we can look at this area and this area. And so that area is 25 minus 3 squared over 25, which is 16 over 5. And so the answer is the sum of these two numbers, which is 16 plus 25, or 0.41. So does anyone have any questions? All right. If not, let's move on to the next question. And so once again, I'll give you a couple of minutes to try this problem on your own. All right, so I'll start going over this problem now. So you have that a10 is equal to 10, and for each integer n is greater than 10, let a of n be equal to 100 a of n minus 1 plus n. And so you want to find the least n greater than 10, such that an is the multiple of 99. And so one of the first things we can notice is an is equal to 100, an plus 1 plus n. This is given. And this is congruent to an minus 1 plus n mod 99. And so a10 is equal to 10, a11 is equal to 10 plus 11, and in general, an is equal to n times n plus 1 over 2. Excuse me for a second. Oh, sorry about that. Okay. So an is equal to n times n plus 1 over 2 minus 45. And so we want this to be equal to 0 mod 99. So basically, the GCD of 2 and 99 is 1. So this can simplify to n times n plus 1. It's congruent to 90 mod 99. And so clearly we can see that n or n plus 1 must be a multiple of 9, because it's impossible for both of them to be multiples of 3 at the same time. So for n is greater than 10, the values of n are n equals 17. And so for 17, you have that this is equal to 17 times 18, which is 9 times 34. Sorry. And if we look at this, and if we divide, also when we divide this by 9, we can see that n times n plus 1 is also needed to be congruent to 10 mod 11. And so when we look at this mod 11, you can see that this is 9 times 1. And this is not what we want. And so when n is equal to 18, it's 18 times 19 or 9 times 38. Please excuse me for another second. All right. And so this is congruent to 9 times 5. And next, after this, we have 26 and 27. And this is 26 times 27, and this is 27 times 28. And this is 9 times 78, and this is equal to 9 times 84. And when we look at these mod 11, they're equal to 1 and 7. And neither of these work. And so now we can look at 35 and 36. And so when we do this, this is 35 times 36, and this is 36 times 37. And so this is 9 times 140, and this is 9 times 148. And when we look at these mod 11, we get that they are 8 and 5. And so this still doesn't work. So we can move on to 44 and 45. And this is 44 times 45, and this is 45 times 46. So this is equal to 9 times 220, and this is equal to 9 times 230. And when we look at this mod 11, it's 0, and this mod 11 is 10. And so these two match up, and so our smallest possible value of n is n equals 0.45. So does anyone have any questions about this problem? All right. If not, let's move on to the next question. All right. Third part of this problem now. So you have that z1 is equal to 18 plus 83i, z2 is equal to 18 plus 39i, and z3 is equal to 78 plus 99i. And so let z be the unique complex number such that z3 minus z1 divided by z2 minus z1 times z minus z2 divided by z minus z3 is real, and the imaginary part of z is maximized. And so we want to find the real part of z now. So we can write z3 minus z1 over z2 minus z1 as a complex number of the form r1 times this. Expand out what the definition of cis of theta 1 and cis of theta 2. And so this is equal to cosine theta 1 cosine theta 2 minus sine theta 1 sine theta 2 plus I times cosine theta 1 sine theta 2 plus cosine theta 2 sine theta 1. Imaginary part we can see is just equal to sine of theta 1 plus theta 2. So now we need that this is real, and this is only true when theta 1 plus theta 2 equals 180k for some integer k. And so what this means is basically that complex, now the complex that correspond to Z1, Z2, Z3, Z are, they form a cyclic quadrilateral. And so we're trying to maximize the imaginary part of Z, and so it must lie on the top of the circumcircle. And so that means that the real part of Z is just the real part of the circumcenter. And so after this, you can just set 1, for example, A to be 18A3, B to be 1839, and C to be 78. And now we can compute their circumcenter. Alright, so I'll start going over this problem now. So we want to consider the arrangements of the 9 numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, and a 3 by 3 array. And so for each such arrangement, we let A1, A2, and A3 be the medians of the numbers in the rows 1, 2, and 3, respectively. And then we let M be the median of A1, A2, A3. And so basically, we want to find the number of arrangements such that M is equal to 5, where M is the median of A1, A2, and A3. So then first we can look at, so first we can look at the row that has the number 5. And so in order for M to be equal to 5, clearly 5 must first be one of A1, A2, A3. And this happens when the other two numbers in the row with 5, for the other two numbers in the row with 5, one of them is from in the range of from 1 through 4, and the other is from 6 through 9. And this is a total of 4 times 4, which is 16 possibilities. And so the total number of ways that we can arrange this row is 16 times 6, which is 96. The number of ways to arrange the 3 distinct numbers. And so now we can look at the other 2 rows. And for those rows, there's a total of 6 numbers, so there are 6 factorial ways to arrange them. And then the number of ways to arrange them is exactly half of this, because the 2 other rows are interchangeable. So they're interchangeable. Okay. And so the number of ways to choose a 9 by 9 grid is 96 times 6 factorial over 2. But we also need to multiply by an additional factor of 6, because the 6 is the number of ways to arrange the 3 rows in the first place. And so up until this point, this number has been counting the rows as if they're already ordered, and this is the number of ways to order the rows themselves. And so this is 96 times 6 times 360. And so when you do the calculations, the number is equal to 200,360. And so we want to find the remainder when Q is divided by 1,000. And so that tells us that the answer is just 360. Okay. All right. If not, we can move on to the next question. And once again, I will give you guys a couple of minutes to do this. All right. I'll start going over this problem now. So you call a set S product free if there do not exist A, B, and C in S, not necessarily distinct, such that AB is equal to C. For example, you're given that the empty set counts as product free, and the set 1620 counts as product free. However, 416 is not product free because 4 times 4 is equal to 16. And similarly, 2 times 2, 8, and 16 is not product free because 2 times 8 equals 16. And so we want to find the number of product free subsets of the set 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we can do some casework based off of the lowest number or the smallest number. And so if the smallest number is 1, you have that 1 times 1 is equal to 1. And this is clearly does not work. So we don't have 1 in any of our cases. And our next lowest number is 2. And in this case, first we can look at the sets 3, 6, and 9. So we can also split this into 5 and 10, and 7 and 8. So for 5 and 10, there are no restrictions other than the fact that you can't have both in the same set. So for 5 and 10, the possible subset you can take from here are 0, the empty set, 5, or 10, which is a total of 3 possibilities. And from 7 and 8, there's 4 possibilities, which is the null sets, 7, 8, and 7 and 8. For 3, 6, 9, we need to be more careful. So we have the null sets. We have the set of 3. We have 6, 9, 3 and 6, 3 and 9, 6 and 9, and 3, 6, 9. And so now we can see that 3 and 6 cannot work because 2 times 3 is equal to 6. And here we have that 3 times 3 is equal to 9, so this set does not work as well. And then here we have that 3 times 3 is equal to 9, and we have that 2 times 3 is equal to 6. And so this leaves us with a total of 5 working cases. So when the smallest number is 2, the total number of product free sets is 5 times 3 times 4, which is 60. And now we can look at when the lowest number is 3. And so when it's 3, the smallest number that has restrictions on it is 3 times 3, which is 9. And there are no restrictions for 3 on 10. So for this case, we can take any of the numbers from the set 4, 5, 6, 7, 8, 10. And so there's a total of 6 numbers here. So the total number of possibilities for this case is 2 to the 6, which is 64. And when the minimum number is not 2 or 3, then in this case, you're free to choose from 4, 5, 6, 7, 8, 9, and 10. And this is because 4 squared is greater than 10, which means that none of these numbers will affect whether the others appear in the sequence or not. And so there's a total of 7 numbers included here. So this case has 2 to the 7, which is equal to 128 possibilities. And so the final answer is the sum 60 plus 64 plus 128, or 252. So does anyone have any questions about this problem? Okay, I guess not. Then in this case, we can move on to number 13. And so once again, I'll give you guys a couple of minutes to do this problem before I start explaining it. Alright, so I'll start going over this problem now. So for every integer, for every m at least 2, integer m at least 2, you let q of n be the least positive integer with the following property. For every n that is at least q of m, there is always a positive integer k cubed in the range n less than k cubed less than or equal to n times n. So we want to find the remainder when the sum from n equals 2 to 2017 of q of m is divided by 1000. And so for now, we can just try some small cases and see what happens. So when n equals 2, you want the ratio between consecutive perfect squares, perfect cubes, to be less than 2. And so the ratio of 64 to 27 is greater. And so what this means is that once 64 is in the range of n is less than k cubed is less than equal to 2m, once 64 falls within this range, for all numbers at least the value of that n, there's always a perfect cube, k. So the q of m for m equals 2 is 32. And now we can look at m equals 3. And similarly, the ratio between consecutive perfect cubes, such as here, is less than 3. And now we have that the ratio of 64 to 27 is less than 3, but the ratio of 27 to 8 is greater than 3. And so what this means is that n is less than k cubed is less than 3n, and this 3n should be equal to 27 to make it minimal. And so in this case, it's 9. And when m is equal to 4, the ratio is less than 4. Less than or equal to 4. And so the ratio between 8 and 1 is equal to 8. And the ratio between 27 to 8 is less than 4. This is greater than 4. So for this one, it's just, the answer is just 2. And for m equals 5, 6, and 7, we can see that the same holds true. 8 over 1 is greater than m, and 27 over 8 is less than m. And so in all of these cases, m is equal to 2. And now, when m is equal to 8, we can see that 1 is less than, when n is equal to 1, we have that 1 is less than k cubed is less than or equal to 8. And now we can see that for all perfect cubes above this, the ratio will always be less than or equal to 8. Actually, no. The ratio will always be less than 8, to be more precise. And so this tells us that q of 8 is just equal to 1. And now from here, we have that m equals 9, and then q of 9 is also equal to 1. And so by this point, we can guess that for all m larger than 8, m at least equal to 8, q of m is equal to 1. So q of m is equal to 1 for m at least 8. And so you can see this is true because we just need to find a value of k. Okay. So we can just prove that the difference between any two consecutive values is much larger than any perfect, the difference between, than the distance between any perfect cubes in a similar range. So the cube root of m minus n minus the cube root of n is at least the cube root of 8 times the cube root of n minus the cube root of n, which is equal to n, which is at least 1. And so this is when n is at least 1, of course. And so this proves that there's a k such that n is less than k cubed is less than or equal to m times n. And so the sum of the numbers from 2 to 2017 is simply just 32 plus 9 plus 2 times 4 plus 2010. And it's because we want this mod 1000, we can take out the 2000, so it's just 32 plus 9 plus 8 plus 10. And this is equal to 059 mod 1000. So does anyone have any questions about this problem? Okay. So if not, I guess that's it for today's class. And thank you for coming. And I guess I'll see you next week.